Hello, and welcome to another episode of the Oxford Online Maths Club. My name's James. Good to have you with us. If you're watching live, I think I'm broadcasting live, and I think you can hear me. Oh my goodness, it's not a good day for tech. Let's find out. We've got some people in chat live. I can see Irene and Marcus are here, and Jamie is here as well. Hi to people watching. If you want to join the live chat, you can join the live chat underneath here. There's a link at the bottom screen or in the YouTube description. One person in chat has confirmed that they can see me, which is fantastic stuff. I am also trying to set up we're supposed to do a poll, right, for how was your day, and like a total professional, I do not have that set up ready to go. We're gonna have that in just a second. In the meantime, shout outs hi to Charles and Casey and Ben, and oh my goodness, Marcus is here as well, and it's all kicking off for this episode of the Maths Club. We're going to clear results on the poll from last. There we go. We got a poll. It's a how was your day poll, and somebody did ask me how my day was as well. I think my day was fine, thanks. It was normal sort of admin day, just sending loads of emails, getting stuff emailed around. Which is my job, so that's all right. Just as a quick check. Okay, cool. And I think I'm joined in chat today by Robin, who's one of our current students, who's helping out for the first time in chat. Hi Robin, if you can hear me and see me, then hey Robin, you're in the live stream too. We're gonna, let's see this. Right, okay. So how's people's days going? People's days are going pretty well. I think that's an average of 3.93. As always, I'm watching out for people who vote for 1 star or 2 stars. Somebody's voted for 1 star. Math Club is perhaps a break from the rest of your day and everything else that's going on, where we can do some maths together. Robin's here. Robin says hey in chat. Robin in chat, this is now a technical behind the scenes note. Hi Robin, if you can hear me. Need to move things to published, not to reviewed. I don't think people can see reviewed. I'm not sure actually. I don't understand VBox. We need to move things to published. Further math was cancelled, sad face, says Liam. What does that mean, Liam? Liam, what does further math being cancelled mean? Is that also, Liam, is that an explanation of 1 star? And it's Liam at the top saying the terrifying news that further maths has been cancelled. Also, I've realised that I'm watching my own live stream in a different tab, so I should close that. Right, okay. I think we're good. It's all rolling. Let's see what we've got coming up today. Coming up, love it when that works. Triangles, more triangles, because people have emailed me more facts about triangles, so thanks. I have a very interesting inbox. There's an email address down there. People have been sending me facts about Pascal's triangle, and I want to show you a new thing that we haven't seen before, called to do with patterns. Is Robin from Brasenose? What a question. Maybe you've met Robin before. Oh, also I put this up. I put this slide in. It says that further reading is going to be posted tomorrow on the website. Further reading is a little bit tricky to write, and I'm hoping that if I put this slide in, then it will force me to write some further reading, so that you can find out more about the stuff that's going on today. I'm trying to sort of guilt trip myself into writing some further reading, so we'll find out. We haven't had further reading yet this season, so we'll see. Okay. Here we go. Some people can see them. More triangles. Yeah, everyone loves triangles. Right, okay. I want to show you this triangle first. I think Charles is in chat. So let's just see. I think Charles sent me this picture because last time we talked about Pascal's triangle again. If you've been watching previous episodes, you'll know that we've been talking about patterns in Pascal's triangle to do with the remainder when you divide the numbers in Pascal's triangle by different whole numbers. Charles has looked at remainders after dividing by 4. Last time we suggested you could maybe colour those in different colours. Maybe you tried this at home as well. Maybe you picked the same colours as Charles, or maybe you picked different colours. Charles has gone for different shades of grey for the different remainders when you divide by 4. So there are these big upside down triangles for numbers in Pascal's triangle that are a multiple of 4. Let's zoom in a bit. Okay, that's probably enough. Big dark grey patches that are multiples of 4, I think. And then some other bits that are not multiples of 4 that are colour coded as well. If you can call. Hey Charles, if you can, if you can see those inside there. I think these bits might be multiples of 2 on this bit of Sierpinski triangle, because I can see them adding up to give multiples of 4, and the only thing that adds to itself. Anyway, this series is so far just Pascal's triangle. Marcus is right. Just Pascal's triangle again and again and again. Because there's sort of an open problem. I suppose it's not really an open problem, I shouldn't say that, but there's something that we haven't really addressed so far. People have sent me lots of pictures of Pascal's triangle, but I don't think people have yet explained to me what's going on in this picture. There's lots of stuff going on. There's lots of patterns. There's lots of other stuff. Is there a deeper reason why the Sierpinski triangle always seems to show up in Pascal's triangle? Sort of, yes. I think my best explanation is to do with those cellular automata that I mentioned in the episode 0. I mentioned in passing. If you remember, we looked at oddness and evenness. What happens when you add things together? Lots of the different systems that we're looking at, the remainders when you divide by different numbers, lots of them behave in a similar way. Or said differently, Pascal's triangle and looking at remainders, you tend to end up with triangles, upside down triangles like this, because inside an upside down triangle like this, these are multiples of 4, and when you add together multiples of 4, you get more multiples of 4 all the way down in a triangle underneath. There's something inherently upside down triangle about this. Good, okay, hello, so someone from year 7. Hi, person from year 7. Triangles, appropriate for all ages. Right, that's the mad stuff. So I really like this picture that Charles sent in. If you are one of the many people who previously made a picture of Pascal's triangle and maybe colour-coded odd or even numbers, maybe you would like to make your own version of this picture with multiples of 4, because I think I've got unanswered questions, such as, let's try and make this concrete. Why? I shouldn't say that, I'm going to make it concrete. How long does it take before you get to a big upside down triangle, the full width? When do those happen? I think we know the answer for when all the elements are odd, or when all the elements are even, except for the ones, I suppose. But maybe we don't know when that happens for multiples of 3 or 4 or 5. I don't think people have told me when that happens. Yeah, and Math Club counts episodes from 0. Which then means that I don't know if I should refer to the first episode or the 0th episode. Discuss in chat. Should I say, as we saw in the 0th episode, or is that just really off-putting? Can I still call it the first episode if I put a number 0 on it? This is what, episode 2 or something, the third one? Feels off, feels bad, but I know from a previous experience that people are very keen on indexing from 0, so here we are. Pascal's triangle, yeah, good, right, okay. That's one thing. Sort of challenge, homework, ongoing, explain this to me. No one's really explained this to me, because look at it. How would you possibly explain this? That's not even a question. Martina, who did some electronics last time, has sent in a sort of challenge, I suppose. This is a picture that Martina sent me, based on last week we had triangles inside squares. If you remember, we had an equilateral triangle that shared a corner with a square, and we tried to make the equilateral triangle touch the other sides of the square. Why am I doing hand motions when I could just redraw the picture from last week? Picture from last week, equilateral triangle that just touches the sides of the square. That is one of the least equilateral triangles I've ever drawn. Martina's done some sums for how to do that in general for other shapes. Here's a pentagon that's just fitting inside a hexagon and sharing a corner. And there's some maths you can do to work out how big to make the pentagon in terms of the hexagon, which you might like to think about if you are keen on geometry, to try and work out how big is this pentagon if the hexagon side length is 1. And something that I noticed when I saw this picture, I suppose, is this pentagon fits and it shares a corner. Is this the biggest pentagon that you can fit inside the hexagon? I'm not sure, because it feels a little bit like you could shift it this way a bit and make it a bit bigger, maybe, or maybe not. I don't really know about hexagons. Maybe not, I suppose, because these points would just slide that way. Maybe that's not true. Maybe I'm being unfair for this solution. Is that the biggest pentagon you can fit inside this hexagon? I don't know. What's the answer for other shapes? You know what I mean? It sort of feels a little bit like maybe we could get away with a bit of space around here, a bit of space around here that we're not using. Maybe we can't use it. We saw some weird solutions on Eric's packing centre last week where things don't fill up the space. People in chat are voting for 0th episode, which I think I'm going to pronounce 0th. There's 2 chat messages and a thumbs up, so that's pretty conclusive. Let me have a look at. I've got at least 1 email has come in telling me, yep, brilliant, cool, right, we're good. If you email me during Maths Club, by the way, there is a tiny probability that I see what you've sent in, and even less chance that I review it while it's happening. Interaction through chat is the best way to get my attention. Right, okay, challenges from last time. Charles has sent me some pictures. Can you make your own pictures? Can you explain why Sierpinski's triangle? Why is it? Is there about to be a big row that's all multiples of 4 or something amazing? If not, why not? And can you fit polygons inside other polygons? Right, okay. Those are some sort of leftover things from previous calculations we've done. Today, I would like to show you, that was triangles, I would like to show you some patterns. The way this works is that I'd like you to tell me when you spot a pattern. And there's going to be several patterns. So if somebody else gets in chat first, don't worry, you can say the same thing as them, you can spot the same pattern, you can maybe describe it differently, but there's going to be multiple patterns, so keep watching out for another pattern to appear in the stuff that I'm doing. I'm going to try and work slowly, so that if you see a pattern emerging, you have a chance to tell me in chat. Okay, does that make sense, chat? It's sort of interaction that, you know, I crave interaction and people telling me what's going on during these things. We're still a little bit lagged because we have a vote for 0th episode is disgusting, which was a discussion from a minute ago. The opposite opinion. 0th episode? That's even worse. Yeah, okay, right, okay. I'm going to take that yo as a sort of, oh no, there's people still arguing about ones. Right, good, okay. I'm just going to start going, we'll see. They would tell me. So Pascal's triangle we've been looking at, it's all about the triangles. We saw it had triangle numbers in it. It had the sum of the triangle numbers, which is the tetrahedral numbers, or triangle-based pyramid numbers. There's probably maybe enough triangles for an entire series so far. Let's think about squares instead. So if you've seen square numbers, they look like this. It'd be very funny to get in chat and tell me that you've spotted the pattern of square numbers. What I'd like to look at is the differences. The so-called difference of 2 squares, which is maybe a concept you've come across before. Here I'm going to focus on the difference between 2 consecutive square numbers. Again, just let me know in chat if you've seen any patterns. Miles has got to vote for a pattern. We're going to go for it. And Miles has put a suggestion for a pattern in chat before it's even appeared on the screen, which is excitingly fast. Okay. Hopefully the patterns start off as something that we can all agree on, and hopefully the patterns end up somewhere where we don't agree, or less obvious. Okay, so Miles called it. Charles wants to use binary. So brave. Yeah, okay, so we've got notions for sequences in chat. Brilliant, okay. So I wasn't quite sure when I was planning this if people would be happy with sequence notation, like 2n plus 1, because I figure there's probably some sort of year 12s and year 13s around who maybe you know loads about sequences, but there's also at least one year 7 and some younger people who maybe aren't so happy with this 2n plus 1 algebra stuff. Anyway, the option's there if you want to. I understand this, but this stuff that people are putting in chat, so successful communication, but I also loved it. Yeah, the difference is odd numbers. Yeah, these are odd numbers. Great pattern spotting. Great pattern spotting team. Let's do the differences again. So this is the lesser known difference of the difference of 2 squares, which you don't learn in school because it's not as important. So the difference of consecutive squares. I suppose it's the difference of consecutive differences of consecutive squares. Is 5 take away 3 is 2, 7 take away 5 is 2, 9 take away 7 is 2. Now I may have suggested that the sequences would get more complicated or interesting as we get on. That hasn't quite happened. this sequence is the difference of the odd numbers, which is, I think, turned out to be a constant sequence. Maybe I should give the constant sequence more respect, right? A constant sequence that's constantly 2 is pretty useful. Yeah, I agree. Anonymous person in chat says looks like 2. Yeah, I'm with you. Good. Right. Okay. The sequence of squares numbers forms a quadratic sequence is a great phrase. I missed that when you said it. Sorry. And Miles says they built it in Minecraft. Well, there's a reason you need this is because anyway. Yeah. Oh gosh. Okay. We'll get to discrete calculus when we get to discrete calculus. Some people learn about the differences like this as part of A level. I think you can do these sort of quadratic sequences at some point in your school maths career. I'm going somewhere with this. We're gonna push it on a little bit. Okay. There is, by the way, a nice sort of geometry thing going on for y squares versus like odd numbers. Maybe some people in chat have seen this before because you're experts on square numbers and the difference of 2 squares. What am I getting at here? There's some nice reason or some nice visual thing you can do with odd numbers and squares that shows that relationship. We've got this kind of difference here of square numbers turning out to be the odd numbers, nice familiar odd numbers. There's something sort of nice picture we can do. Oh my goodness, we're doing discrete calculus in chat, which is where I was maybe going to end up in about an hour's time. So these are in GCSE maths, brilliant stuff. Oh, okay, I'm out of touch. Everyone's already done some GCSE. Yeah, it's like differentiation. Yeah. Put the sequences down here. N squared, this is 2n plus 1, and 2. Cool, okay. Okay, yeah, there's a thing with dots. I guess it's a bit hard to describe in chat, isn't it? But there's a chance that somebody hasn't seen this before, so I'm going to do the thing with the dots. Well, actually, I like doing it with sort of pictures of squares. Let's see if I can do this. I've got a square grid here. Very faint, but I'll draw over it. I like to do things on here, by the way, that there's a good chance you've already seen before, because quite often the first time you see something, or even the second time you see something, you're at the state of sort of accepting it, or memorizing it. And returning to things to make sure you understand them and can apply them is sort of a different skill. It's valuable. I guess this is a defense for why I'm telling you about GCSE maths. What are we doing? Here's 1. I'll put the dots in as well. Here's 3. Kind of fitting around the outside to make the next square number. And then 5 around the outside. The next odd number to make the next square number. The difference to 2 squares here, difference to 2 consecutive squares, behaving like the odd numbers going outwards. It's something I can't remember when I first saw this picture, but yeah, this is the thing with the dots. So that's good, and you can extend this pattern, of course, to get more of an understanding of why the difference of consecutive squares is odd numbers. Okay, that's all very good. Apparently we learn this in GCSE. We do quadratic sequences or something, and people have seen this before. Let's do cube numbers. So cube numbers are, you take the numbers and you raise them to the power of 3. So I think you get 1, 8, 27 is 3 cubed, 64 is 4 cubed. Never try to do maths on the stream. Oh my goodness. Consult notes. Consult notes. No, we're good. And I thought we'd do differences again. Oh, chat's fast. Chat's real fast. Again, the rule is let me know if you see a sequence that you've seen before. Last time we played this game, the odd numbers fell out. This time, I've got a sequence that goes 7, 19, 37, 61. Somebody in chat's telling me 7 cubes. Thank you very much. In a second, I'm going to have to do some hard subtraction, aren't I? 216 taken by 125 is, I think, 91? Yeah, I think it's 91. And then I don't really trust myself to do this subtraction, but if you're playing along at home, as I sometimes encourage people to do. If you're playing along at home, then you might like to work out 343 take away 216. I probably can. I just don't feel like doing it right now. Any takers on what's going on? This arithmetic is crazy. 127. Yeah, I buy that. Okay, I buy that. That sounds good to me. Love that. We want to take this? But people in chat have been pretty switched on to naming. Thank you, everyone. Oh, look, subtraction. Thank you. Some sort of quadratic sequence. People think. Thank you, Marcus. Seen these numbers before? So it's a suggestion for a formula, which is amazing. Well done. I think it is a quadratic sequence, and I think that is the formula for it. I kind of want to know where you got that from. 3n squared plus 3n plus 1. Is it just sort of obvious to you that it's 3n squared plus 3n plus 1? Have you got a method? Have you seen this sequence before? Do you know what this sequence is? So the last time we did this difference operation, we got the odd numbers. There is a nice name for this sequence. Somebody out there is probably typing it into OEIS right now, because the online encyclopedia for integer sequences has a search feature where you can search for a sequence based on what the numbers are. The online encyclopedia for integer sequences turns up quite a lot on Numberphile, which is a very good YouTube channel. Someone searched it, or did they look at the differences? Oh, someone's expanded it to look at the difference between n plus 1 cubed and n cubed. I see, because you know the formula up here. You're doing... So people who saw the phrase discrete derivative earlier, hey look, there's a difference of 2 cubes. That's very nice. Okay. Okay. So we know what this is. So now I've seen that you've done it by multiplying out. Fine. Okay. You've got the algebra done. Have we got a geometry way of thinking about what this is? No one's quite said the differences between the differences have a difference of 6. Okay, so someone at home, I love this, someone at home has gone down and worked out the next rows down. I'm being really slow because I want to focus on this sequence first, but yes, if you keep on working out differences, that is where we're going. Divide this by 2 and subtract this from the differences. Wow! You don't quite mean divide those numbers by 2, they're all odd. Are they all odd? They look odd, don't they? I guess cube numbers alternate between being even and odd, so the differences are always odd. Yeah, okay, something about cubes and something about hexagonal numbers. Brilliant. Okay, yeah. These have got a name. These are called the hexagonal numbers, the centered hexagonal numbers. I'll show you why. The geometry idea is to draw a cube and, oh gosh, which is easier said than done, and then to imagine extending that cube out in 3 directions, which I'm going to try and do this way. I need some dotty lines, there we go. Extend it out this way, and extend it upwards as well. And then I've got to try and draw that mess of extra stuff. Oh, not quite there. I want to go out a little bit further, don't I? Save me, Myro. A little bit further, and down like that. Okay, so Marcus has probably seen this in Minecraft for when you've built a cube and then you wish that your cube was slightly larger, you might need to go around 3 of the sides and expand it outwards. Not my greatest picture, but you know what? Not my worst picture either. That's kind of the side, this is the top. This is the face over here. Okay. 127 isn't prime. Does someone suggest they were all prime? 91's not prime either. It'd be good if they were all prime, wouldn't it? Because then we'd have a big sequence of primes. Oh, is 127 actually prime? Oh gosh. If I've been double got by chat. Now I think 127 is prime. I've got really confused. Similar to the square but with a cube. Brill. There is a reasonably nice way to turn this into a hexagon. So, as advertised, these are called the centered hexagonal numbers. 2 questions. What on earth is a centered hexagonal number, and what on earth has this got to do with hexagons? 127 is prime. And look, this is the duality of chat. They're telling me 127 is prime, and also that it's not prime. simultaneously. What do I do with this information? I can't divide by 7 fast enough. Okay. The relationship, by the way, maybe someone in chat will tell me. I'm enjoying this. Relationship, by the way, is something to do with cubes and hexagons. Like we had a relationship between squares and odd numbers. There is a relationship between cubes and hexagons. Good. Okay. So suggestion from chat, which I like. Collapse that extra bit. So if you sort of rotate the picture around a bit. Cube has 6 faces. That's true. 6 of the edges are interesting to me, actually. If you rotate this around so that we're looking at this extra bit, putting extra stuff on these 3 faces. Cube's got 6 faces, but we're only really using 3 of them. Here's the hexagon. If you look at a cube diagonal on, it looks like a hexagon, because you can see these 6 edges around the outside. And if you go and fill in some dots or something, I'm not going to do it here, but if you fill in some dots, then you can convince yourself that this extra bit that's been wrapped around the cube, if you look at it right, it is a hexagon. Maybe we should try and put some dots in. It's quite a pretty picture because hexagons are great, and this is a sort of hexagonal grid. Yeah, cool. Collapse that extra bit you've drawn. If you look at it from the right angle, you can see the hexagon. It's a little bit like if you looked at this one from this angle. That's an eye looking at it. From that angle, you'd see a row of odd numbers. This one is all about looking at it from the correct angle. So we had to do these in like physics class or something, where you had to draw like eyeballs looking at your science. The tricks with little eyelashes on, so that it was even weirder. Right, good. Okay. Hexagonal numbers, pretty good. I like those. I like the link to the geometry as well. Let's put that picture slightly down a bit because it's time to see the differences. Chat already told me what you think is going on down here. So let's see if we can get that to work. I quite like this as a way to predict what the next cube number is, by the way. It sort of works. Like I can sort of see, if I can't be bothered to cube things, but I'm okay with adding, then I could generate the next bit over here to work out what the next cube number is, because I've spotted a pattern down here. Aha! The second difference quadratics, brilliant. Meta pattern detected. Anonymous person in chat here. The first one was 2 at the bottom. This one ends in 6s down the bottom. Okay, the people who know about discrete differentiation, you can prove that at home. People who don't know about discrete differentiation, hey, we should try this for other powers, right? We've tried square numbers and cube numbers, we should try the powers, see if it keeps happening. You can use this method to work out a formula for the sequence. That's a good idea. I suppose I know, formula for, maybe a formula for this sequence, right? Maybe that's what you mean. Yeah, something like that. Yeah, okay. Because you learn this thing about, all 6s, yes. You learn this thing about quadratic sequences at some point, right? How to do this adding up. Hiding in here somewhere, there's an idea that, I had this idea that we could use this to work out the, use this to work out the formula for the sum of the squares of numbers. It's sort of hiding in there. Now, maybe at home you know the formula for the sum of the square numbers. It's quite a good formula. I think you learn it at some point. I mean, like 1 plus 4 plus 9 plus 16. There's a formula for that to tell you how much the sum of the squares is. It's quite a good formula. That's a related fact to what's currently on the board. Now, I kind of know a way to untangle this to make it into a fact about the sum of the square numbers. I wondered if chat had any opinions on how to do that first. Let's put this slightly on the screen like that so we can see the diagrams and the title all at the same time. This is something to do with the sum of square numbers. Yeah, that formula. I know that formula. So it's 1/6 n, n plus 1, 2n plus 1. I have a preferred way to write it, which is, this is what it looks like in formula booklets, with the 1/6 and the n, n plus 1, 2n plus 1. I find it easier to remember as n, n and a half, n plus 1 all over 3, but maybe that's just me being weird. I've divided top and bottom by 2. That doesn't mean anything, that pattern doesn't continue, but hey, yeah, there it is. Fantastic video on this somewhere, can't find it, otherwise post the link here. Miles, if you find it, let us know. Sounds like good content for further reading, doesn't it, man? Apparently I've got to write some further reading now. Yeah, like sum of the second row, right. So we've got something like, we know a formula for the second row because of this difference of two cubes algebra. And then what we're doing to get from, if we wanted to get from the second row back up to the first row, we want to add together lots of these squares. Oh, no, people are not happy with the n. At least one person in chat is not happy with the n, n and a half, n plus 1. I've noticed that maybe the sum of the first n cube numbers, hey, maybe it's always a square number. Yeah, I think that's true. Because I think I learned a formula for the sum of the cube numbers as well at some point, and it's a very good square number. Question, nobody tell them in chat. If you already know, nobody tell them. Question for you, what's it the square of? Work out, you've got a series of square numbers, I think. Write down the square roots. Nobody tell them in chat. I don't understand how you got the n stuff. Oh, okay, so algebra-wise, people are thinking about describing the number 91. Let's do an example by calling this n cubed, where like secretly n is 5, and calling this thing n plus 1 cubed, where I guess secretly n is still 5, and then doing the difference. And along the way, to simplify things, they've multiplied out n plus 1 cubed using, I think that's the binomial theorem, is what that's called, to multiply that out, and then subtracting off. So if you do this expression, subtract off the n cubed, you get this expression 3n squared plus 3n plus 1, which is almost all the terms. Okay, so I quite like this idea that we can maybe add these. I really hope that person who noticed that the sum of the first n cube numbers, they're off doing their own thing. Not related to what's on the board, really, because they're on the next one, but I really hope they write down the square roots of the sum of the cubes. You've got to let us know as well once you've tried it. It almost sounds more fun than the thing I'm about to do, which is to write down a formula for n cubed. That sounds like a lot of work, doesn't it? Okay, right. Sketch ideas. We're going to do the ideas of this rather than all of the details. Some people hate it when I just give you the ideas because it feels a bit like being given homework to go and fill in the gaps, but that's exactly what I'm doing. Okay, so here's my plan. It's a bit stupid. It's something like, if you add all of these numbers together, I've already got a pinch box, let's use a different colour. If you add all of these numbers together and also add 1 at the start, then you get 125. Because you start at 1 and you add all of the differences. That will give you 125. I can try and write that down with algebra. The way I would write that down with algebra is to say that n cubed, let's try and do this over here, is equal to 1 plus the sum, my goodness, this is sum notation for people who haven't seen this before, of this expression. So, right, gosh, quite a lot going on here. Oh, n minus 1, I think, maybe. Gosh, what a complicated thing to throw at you out of nowhere. So the big sigma symbol means add together. over the following values. It's a bit like a for loop, if you've seen a for loop before, with adding together the results as you go through. It says start at m equals 1 and go all the way up to n equals 1, increasing m, so m is 1, 2, 3, 4. And each time, plug m into this formula and add up all the results you get, which means calculate the series 7, 19, 37, 61, all added together. And I think I want to go from 1 up to m minus 1. Okay, brilliant. 1 is included if I sum from if I sum from 0. That's true. Do I like that? Like that a bit, I think. I like that a bit. Yeah, alright, okay. I start my series at 0. How do we prove that? Yeah, so I suppose this is a telescoping differences kind of fact, which means that maybe it's time. Yeah, why don't I go to m minus 1? Yeah. So I think I've gone to m minus 1 because to get to the 5th term along the top here, 1, 2, 3, 4, 5, I only want to use 4 of the terms in this difference sequence. The differences live in between. So although I'm going up to the 5th term, n cubed, 125, I only want the first 4 terms of this sequence for the differences. I think n equals 0 does make it harder to visualize. Once again, we are debating whether to start at 0 or 1, and in this case I feel like starting at 1 makes it easier to explain, at least. I'm starting at the number 1, the very first cube number, and adding on all the differences, treating them separately. I think you're right that it doesn't make a lot of difference to treat them separately. The triangle numbers are the square roots of the sums of the cubes. Correct. What a great fact. Brilliant stuff. Okay. So if you'll let me write this down at the bottom, so the sum of that difference sequence, which is the hexagonal numbers, adding up hexagons gives you cubes. What a crazy fact. But adding up hexagons gives you cubes. We can do a little bit of sort of A-level rearrangement on that statement to turn it into something just a tiny bit more interesting, just a tiny bit more useful, which I'm going to do like this. 1 plus 3 times. So this thing that I'm adding up has got lots of separate terms in it because it's going from m equals 1 all the way up to n minus 1. So there's loads of terms added together here. But each one individually includes lots of separate terms, including this one, which just says every term that I write down as I'm changing m includes this 1 at the end. So maybe I can add up the 1s separately. Addition is commutative, so I can do this. Okay. Start at 1, vote from starting at 1. Cool. I wonder if anybody's voted for episode 0. Episode should count from 0, but this sum should count from 1. It's okay to have different opinions for different contexts. Okay, right, cool. Outline of what's going on. Cube number is the sum of the first cube number plus all the differences so far, which we've got some formula for. We can rearrange that, and then the thing I'm really interested in is this. Sum of the square numbers, that's what this term means. Add up 1 squared and 2 squared and 3 squared and 4 squared. Add all of those together. Now I know what this is. I'm happy about this term, and I'm very happy about this term because this is just the sum of some things up to 1. Sum of 1, a load of 1s. So my plan, I think, is to rearrange all of this, and I'll get some expression for squares. Okay. Quick recap, because at least one person's just joined and we're thinking about expanding out brackets and stuff. We've been looking at the differences between sequences of numbers. We did square numbers first. We saw the differences of odd numbers. We had a geometric reason for that. And then the difference between the odd numbers is the constant 2 sequence. Then we tried cube numbers, and we found that the differences was quite a complicated sequence. We used some algebra to work out an expression for that. People in chat calculated this n plus 1 cubed minus n cubed, which I think they did by expanding with the binomial expansion for n plus 1 cubed. That's pretty good. So it's n cubed, 3n squared, 3n plus 1, and then take off that n cubed, and you get this nice expression. The direction I'm trying to steer us is we could think about adding these things back together, which is like saying a square is made up of a sum of odd numbers. A cube is kind of made up of a sum of hexagons. These are hexagonal numbers. If you write down the algebra for what that looks like, it says that this cube number, one particular cube, can be thought of as built of lots of hexagons, and then algebraically we can rearrange those things to try and get a sum for the square numbers, which is something you learn in school. And I vaguely remember the triangle numbers being given a nice reason why the triangle numbers were true, but I don't remember being given a nice reason why the sum of the square number fact was true. Let's give this a go then. So sum from 1 up to m minus 1 of m's, that's something to do with triangle numbers. I think that is n minus 1 n over 2. And the sum of a load of 1s from 1 to n minus 1 is that. 3 times, I don't know what this is, but I'm interested in it. And there's a 1 over here, which I suppose is going to cancel that one. And then I think I can do some rearranging. I'm saying this very cautiously, just in case it turns out that I cannot do any rearranging. And I want to divide by 3. Yeah, I'm going to rearrange. Yeah, rearrange it. What they said in chat. Yeah, that. Modulo whether I simplify it as I go as well. Let's do it in 2 steps. It's very tempting to just go for it, right? This is, in some sense, perhaps quite disappointing mathematics. Maybe not what you tuned in to see today. And that's the end of the sentence. No. This is maybe some disappointing maths and not what you tuned in to see today. But what I'm about to say is that you can do this not just for the sum of square numbers, but in general for the sum of some powers. And that's quite powerful, pun intended, because being able to sum powers or have a way of generating this formula for summing some powers lets you do lots of other calculations, like summing general polynomials or something. Okay, have I factorised this question? Factorised this correctly? Yeah, you'll get Pascal's triangle again. We cannot escape Pascal's triangle. These numbers, as Charles has pointed out, 1, 3, 3, and there's secretly a 1 here, is a row of Pascal's triangle. This season is themed around Pascal's triangle. That's not intentional, it just happened. I've got 3n minus n, that's 2n, and I'm considering factorising, but I'm scared. I think this is going to differ a little bit from the traditional formula in the formula booklet. I have missed a 2 because I wanted to put everything over 6. Yep, chat's going to catch me up now. Hi Guy. Showing about the train delays. Guy put in chat that they were having train delays. Okay, I can factorise that if I believe in myself and I look at my notes. Now this might not be quite the formula we wanted because it's the sum up to n minus 1, whereas maybe you've learnt the sum up to n if you're doing A levels and you've learnt a sum for this. But hey, it's not bad, right? We could add on if you really want to, you could add on n squared to both sides, and that would make the sum on the right go up to n, and the one on the left would rearrange it a bit. I'm not going to trust myself to do that rearranging now, but probably we get down to the formula you're expecting. Okay, so we can do this for other powers as well. If you want a formula for the sum of n to the power k, p, n to the p or something, then the steps are as follows. The steps are as follows. Write down the difference like this, write down an expression for the differences, and then re-express your power as the sum of those difference sequences, plus 1, or start your sum from 0. So you'd have a p in here, and you'd have loads of terms inside here. Then the sum you're going to get is the sum of the powers 1 down, I suppose. So this is a method for finding the sum of the powers 1 down. you're going to get that. You'll also get some sums of lower powers, because your expansion from the binomial expansion will have lots of smaller powers in it. So, oh my goodness, you've got all of these lower powers, work out all of those first, and then rearrange everything, and you will get, so here I had to know about triangle numbers in order to rearrange it to get an expression for the sum of squares. Now I'm armed with a formula for the sum of square numbers. I can go and write down an expression involving fourth powers, and I'm going to get down to an expression for the sum of cube numbers if I go in that direction. Kind of like induction. Oh, Mark has given a summary. Different sequences and patterns from cube and square numbers. I think it's maybe more obvious what's going on if you try it yourself. So if you have been following along or not following along, something you could try is to try and use this method to generate an expression for the sum of the cube numbers, which is, someone in chat spotted the sum of the cube numbers is really nice. It has an unreasonably nice answer. So the sum of the cube numbers is really good, and for that one I would use powers of 4. So I might write down some differences first for fourth powers, differences, and then differences and differences, and maybe differences again, which might be the number 24 at the bottom, if that factorial pattern holds up. One person told me about a pattern across these patterns, 2, then 6, then maybe 24 next for powers of 4. Maybe it's 24 at the bottom. But anyway, replacing the 3's in here with 4's and doing the binomial expansion again might be a way forwards to get an expression for the sum of the cube numbers. And if you're feeling very powerful, then trying to do something like this for general powers, for power p+1 or something, if you go down that rabbit hole, then you will eventually bump into an amazing sequence called the Bernoulli numbers. So today's episode is inspired by one of my students mentioning Bernoulli numbers in passing, and I thought, the Bernoulli numbers are really cool. I should do a maths club session on them. And then I looked into it and decided, no, I probably can't do a session about the Bernoulli numbers, but hey, I could do this and then tell them the Bernoulli numbers are nearby. Miles is quite keen on discrete integration. I think some other people are as well, but I've singled out Miles because you're at the top of chat. Discrete integration, do you want to do the basics? Do you want to say what that is? I kind of want Miles to explain what discrete integration is. I can remember what discrete differentiation is. Not sure I'm going to do a good job of explaining discrete integration. Sum of n for p is always a bit like, it's a bit like if we integrated n to the p+1 over p+1, but then the rest is different. That's a good observation actually. That this thing at the front kind of looks like an n cubed over 3, which is what you get if you integrate n squared with respect to n. I just want the calculus is hiding in here somewhere. We've got calculus, geometry, and numbers, kind of trying to live together. We want to integrate do discrete calculus. Something powers of 1. We see a 2 in denominator. Something powers of 1. Miles posted a video ages ago. That's true. We should stop watching this video and watch Miles' video instead. Here's a trick that I like for spotting patterns. Sometimes it's helpful to go to the next one down and look for the patterns there. Sometimes it's helpful to go back a step. I started with square numbers because I don't think anyone would have taken me seriously if I'd started with the real first case, right? The real first case would have been to write numbers on the board. Squares are like the second case because they're second powers. The thing I should have done is to write the numbers on the board and then talk about the differences being 1, or as we might say the constant 1 sequence, or the one with the formula 1. In discrete differentiation terms, the discrete derivative of n is 1, or in a binomial expansion terms, n plus 1 take away n is equal to 1. But I don't think you'd have taken it very seriously if I put this up first as the very first sequence. Oh, this is evidence for the person who said, is it factorials? 1 factorial is 1. So this fits your pattern. So sometimes checking a pattern going to the next term is very tricky, but maybe going back a step and looking at an easier problem that you overlooked might be a way to look at this. This is like powers of n to the 1, like how square numbers are n to the 2 and cube numbers are n to the 3. You might even want to go back another step. Today's episode has on several occasions featured the distinction between starting at 1 or 0, and the sequence is a bit weird. It's already the constant 1 sequence. So actually maybe that breaks the factorial thing, because 0 factorial isn't 0, right? 0 factorial is 1. So maybe we need to start from 1 in order for the factorial observation to hold up. Okay, this is very cheeky. I don't think anyone's going to take that seriously, but I am trying to make a serious point about whether you start at 0 or 1, and how going backwards can sometimes be helpful for spotting meta patterns. Right, cool. Serious point disguised with some completely ridiculous mathematics. Yeah, 0 factorial is 1, so that's really disappointing, right? Because the factorial fact is true going forwards. Sometimes you make a problem too simple, I suppose. Right, okay. Really fast discrete calculus. Don't really know what I want to do here. I kind of want to just point at Miles' video. Let's all go and watch that one. Let's do 5 minutes of discrete calculus, and then why do the sum of n to an even power have a factor of 2n plus 1, and for odd powers there's an n plus 1 squared? Does that pattern even continue? I suppose why it does, I think. This is a conjecture, because it's about other powers. Maybe it's true. Maybe you've proved it, sorry, but it's not a fact I know. Factor of n to the even power have a factor of 2n plus 1. Don't have a good answer. Have you looked up or generated a lot of them? Could be something to generate, right? Negative powers. Sums of negative powers. It's a bit of a thing. Anyway, so if you go back too far, you end up hitting some lovely maths. Some absolutely lovely maths. We don't really have time, but if you go to sort of -2 or something. Anyway, never mind. Sorry. Sums of other powers is a whole thing. There's a Riemann zeta function hiding in here. Let's talk about discrete calculus really quickly. So regular calculus talks about limits, talks about functions. This is my understanding based on not researched or prepared mathematics, really sorry. Regular calculus talks about limits, talks about finding the chord. You have a function, and you look at the chord, and you look at what happens if you move that point really close to the first one until the chord line gets really close to being the tangent line, so that as the clear point moves towards the filled in point, this tangent line will start to look like, the chord line will start to look like a tangent line. That's the essence of differentiation, right? Discrete functions are ones that are defined on the whole numbers. So they only have values for whole number inputs. They look kind of like this, I suppose. Let's equally space them so that it's a bit prettier. And then you can't really do the same thing, right? You can't really take the limit because you can't get very close if your function's only defined for whole numbers. So here my input is like whole numbers 1, 2, 3, 4, sort of sequence rather than a function. But you can still think about the difference, right? You can think about the difference between terms. So like to go from that term to that term. You can still think about the change between terms. Yeah, cool. The change between terms. So that's nice. Sometimes people write things like this for a difference between terms, and then people can even work out sort of something that feels a bit like the second derivative by doing a kind of difference of those differences. There are some really interesting effects to do with how well these things approximate the actual derivative to a function if these are points sampled from a smooth curve. The second derivative expression, people usually write down, you have some choices, because to find the second derivative, or to approximate the second derivative, you could look at 3 points, one to the left, one to the right, and this one, and try and imagine finding a kind of difference of those differences. Or you could just look at the previous points, which is like us looking at differences going backwards. Or you could just look at forwards points, to just look at 3 points over that side. And in any case, you're thinking about doing difference of differences. Anyway, and some people do that for the derivatives as well. So you have actually a choice. Maybe you want to use xn plus 1 minus xn. Or maybe you want to do something different to, in some sense, approximate what the derivative would be at that point. That is my take on discrete calculus with no preparation and having not studied it for absolutely ages. Yeah, people got that. I was talking about sums of 1 over numbers. Do you want some facts? Do you want some facts to round out the hour? Let's do some facts. So using this sum thing, and let's sum all of them, why not? So these are other ones you can work out, where this time they're fractions. We're using kind of negative powers to add up powers where you take n and you raise it to a negative power. In the first case, -1, second case, -2, -3 in the third case, -4 in the fourth case. These are quite interesting. They have a variety of different outcomes. This one doesn't converge, which is, I guess, a technical way of saying that sum keeps getting bigger and bigger. That as I keep adding in more terms, well, the sum can get bigger than 10 if I take enough terms. It can get bigger than 100 if I take enough terms. If I take a lot of terms, the sum can get as big as 1,000 or more. So it can sort of keep going. These are really good. That is divergent. I'll put divergent in there. There was a movie called Divergent quite a while ago, but I don't think it was about sequences, so never mind. Okay, maybe that feels a little bit like it should obviously diverge or go off to infinity, because the terms are all positive. So as you add in positive terms, it keeps getting bigger, right? So maybe it's obvious that it should go to infinity. In which case you'll be really surprised to learn that this one doesn't go to infinity. This one is pi squared over 6, which feels implausible somehow to have a pi squared in there, but hey, true fact. The more of these terms you write down, it just gets closer and closer to pi squared over 6. So there's something inherently different going on about those things. This one at the bottom, I don't know if people know this generally or not. I think this should be more famous. It's pi to the 4 over 90, which is quite a good fact. We prove both of those two during the first course of a maths degree, so that's quite nice. There is a really good number file video about the pi squared over 6 one. Where is the circle? Where's the circle? Tell me where the circle is. There's an excellent number file video about that. That's going to be a link in the further reading. Pi to the 4 somehow even more surprising to me. Really hard to explain why in a quick way, right? If you've seen it before, then take a moment to reflect on how that's not a normal kind of result. That's a good result. But maybe this middle one is the most interesting one, because this converges, but nobody knows what it converges to. This one doesn't go to infinity, it's going to some number, but nobody in the world at time of recording can tell you what that number precisely is. You might expect it to be pi cubed divided by something, and I think it's unknown whether it is pi cubed divided by something nice, or maybe multiplied by some rational number. I don't think we know very much about this limit at all, but unlike the film Mean Girls, the limit does exist. We just don't know what it is. So yeah, good. Okay. So somehow there's a sequence here where on the left things look nice and sensible. There's different sums we might try with different powers in. And on the right, the answers are no, that question doesn't make sense. Pi squared over 6, nobody knows. Pi to the 4 over 90, which in itself is quite an interesting sequence. Okay. We've got a good technique for the even powers. We're really good at even powers. We've got a good technique for them, but I don't have time suddenly. The even ones, yeah. The even ones involve even powers of pi. The odd ones, we don't have a good technique. The technique that we have kind of inherently involves squaring things. That's such a terrible thing to say. That's the least mathematician thing I've ever done. Yeah, Euler had a go at this. Euler kind of proved that it converges to pi squared over 6. Proof's not Euler's best proof. It's a little wobbly. Oh, there you go. Either somebody's Googled it or done some calculations. I'm going to choose to believe that it's calculations. There's the number. This is the weird thing, right? We know what the numbers, we know what the digits are. We can calculate loads of it because it's just adding together 1 over n cubed. We just don't know what that number is. I mean, there it is, but what is going on? I think the thing to Google, well, there'll be a link in the further reading to find out more about that, I think. I'm going to leave it there. We've looked at some calculated by hand, hooray! Oh no. Hooray! I'm going to choose to believe that. Really quick maths. Today we've looked at the sum of numbers, briefly looked at the sum of a whole bunch of ones. We've looked at the sum of square numbers via cubes and hexagons and geometry, and something called the binomial theorem. Notes in the further reading. We've quoted some random results that people learn about later on. Robin is from Brasenose. Somebody asked that earlier on. Maybe they've met Robin on a different thing. We can sort of get it from the Riemann zeta function. We just don't have nice answers for what the value of the Riemann zeta function is. Like, we have an answer in terms of the Riemann zeta function, if you'll accept that, but you sort of shouldn't accept that. Oh, we know it's irrational, do we? Oh, brilliant. Good. I didn't know we knew it was irrational. Research. Right, okay. We're going to call it here. What am I planning for next week? I am planning to hopefully at some point get some students on the show. So it's not just all me in the corner telling you about random maths things that my students have suggested. Hope to get some students on the show. Thank you to Robin for moderating. Thank you to everyone for watching. We're going to be back next week for, gosh, something else. Possibly tilings, so possibly more triangles. In the meantime, if you want to send in your explanation of why Pascal's triangle do that, how big you can put one polygon inside another polygon, or your own attempt at finding patterns within patterns within patterns for differences within differences within differences, then please do get in touch on the email address at the bottom of the screen and in the YouTube description. I've been Jason Ray. Thank you for watching. We'll see you in 167 hours for the next episode of Oxford Online Maths Club. Bye. How do I? Yes.